Welcome to this explainer. Okay, let's dive right into this fascinating shift in AI architecture. We're talking about moving from fragile, delicate prototypes to systems that actually use chaos as fuel. Look, if you're building or scaling intelligent systems right now, you already know the pain. You have this model that works absolutely flawlessly in a perfectly sterile, controlled demo environment, and then it almost instantly crumbles the moment it hits the messy, unpredictable reality of production. Today, we are going to explore a completely new paradigm called anti-fragile AI and look at how it fundamentally changes the way we architect intelligent systems. 70%. Seriously, let that sink in for a second. That is the massive failure rate of AI projects trying to reach production right now. It perfectly validates that frustration so many of us feel. I mean, you spend months building this sophisticated agent logic, and then, boom, you hit a brick wall. Why? Well, because the system is built for a world of predictable inputs and stable conditions. And let's be real, that world simply doesn't exist when you deploy at scale. So here is how we're going to break this down today. First, we'll look at why AI systems fail. Then we'll define anti-fragile AI, dig into the core architectural principles, talk about building intelligent guardrails, and finally wrap up with the enterprise AI advantage. Starting with Section 1, why AI systems fail, and specifically the optimization trap. What's really revealing here is that production failures are rarely about the model's core intelligence, right? We aren't looking at failures in language comprehension. We're looking at behavioral and structural breakdowns. Take that staggering 42% failure rate just in tool calling. That's not a lack of intelligence. That's an agent completely hallucinating a JSON schema or passing a string to an API when it strictly expects an integer. And another 31% is due to invalid formatting. So the model's reasoning might be perfectly fine, but its execution framework is just incredibly brittle. A lot of this breakdown comes down to something called state drift. Think of it literally like driving with an outdated GPS. The agent's internal reasoning is perfectly coherent. Like, its internal logic makes complete sense to itself, but it has completely lost touch with the shifting reality of the external environment. It's effectively hallucinating its current state and making decisions based on a reality that has already shifted. And where does this state drift come from? It fundamentally stems from a stable conditions bias. See, we train these systems on low variance historical data. We implicitly assume that future conditions are going to strictly mirror past conditions. But the second an API endpoint drops unexpectedly or user behavior spikes with massive volatility, the system, which was highly optimized for pure efficiency, just shatters. Which brings us to Section 2, defining anti-fragile AI. This is where we flip the script entirely and learn to use chaos as fuel. So rather than looking at disruption as this annoying noise that has to be filtered out or just somehow survived, anti-fragile AI recognizes that chaos is actually highly valuable data. Disruptions actively strip away artificial constraints. They reveal hidden optimization paths that you would honestly never see in a perfectly stable environment. It's about treating errors not as fatal crashes, but as the absolute primary fuel for continuous system evolution. There's a really stark contrast here. Historically, engineering has aimed for robust AI. That's a defensive posture, right? You're just trying to hold the line and maintain a baseline of performance when things get tough. But anti-fragile AI? That is entirely offensive. We are architecting systems that emerge stronger specifically because of the disruption. The storm doesn't just pass over them. The storm literally powers them. All right, let's move to Section 3, core architectural principles. Let's look at how we're actually building this engine under the hood. To construct this, you really need three main pillars deeply integrated into your agent's core design: dynamic learning rate adaptation, adaptive goal reevaluation, and the self-healing optimization loop. This is how you shift from static, rigid logic to a probabilistic, self-improving architecture. Let's zoom in on how the system reacts to dropping confidence. In a traditional setup, when prediction accuracy drops because the environment goes crazy, it throws a timeout error or defaults to some conservative fallback. An anti-fragile system does the exact opposite. Through dynamic learning rate adaptation, it aggressively dedicates compute to discover new patterns. It senses the variance and essentially says, okay, the rules are changing right now. I need to absolutely spike my learning velocity. And this creates a really elegant self-healing optimization loop. Imagine replacing that incredibly tedious 3 a.m. process of developers grepping through logs trying to manually tweak prompts. Instead, a meta-level agent is constantly analyzing the observability traces for error patterns. It finds the root cause,
formulates an improvement, and then autonomously patches the system's prompts or tool schemas in real time.
Now, Section 4, building intelligent guardrails. Because obviously, we need safety in autonomy.
Because look, if a system can learn, it can absolutely learn the wrong lessons. You must architect intelligent guardrails and circuit breakers to ensure runaway adaptations don't somehow violate your core business logic. So we're talking about real-time constraint validation, detecting statistical anomalies in how the agent is behaving, and deploying automated rollback logic if a new strategy fails. And of course, having a clean, human-in-the-loop escalation path. To anchor all this safety, you use what's called a golden dataset. By codifying these novel failure modes and validated interactions into this dataset, the system develops a sort of behavioral memory. This is crucial. It ensures that an isolated failure, once it's solved, prevents regression and becomes a permanent safeguard. Basically, the system never makes the same mistake twice, locking in the gains from every single disruption it survives.
So we've looked at the failures, the architecture, and the safety mechanisms. But what does this mean for your organization at a macro strategic level? Ask yourself, what happens when disruption literally becomes your competitive moat? That brings us to Section 5, the Enterprise AI Advantage. Let's look at these offensive AI capabilities.
What's fascinating here is how our success metrics fundamentally flip. We stop measuring mere survival, things like time to recovery or how much it costs to retrain a broken model. Instead, we start measuring the speed and the quality of our adaptation. We're looking at learning velocity during uncertainty. We measure the actual business value extracted per anomaly. The disruption itself literally becomes a KPI of opportunity. And because of that, your speed of adaptation becomes a sustainable competitive moat. Imagine a massive market shock happens. Say, a major API updates overnight. Your competitors are completely scrambling, their AI is throwing errors everywhere, and they are manually trying to patch their brittle systems. Meanwhile, your anti-fragile architecture is already absorbing the new data, it's extracting proprietary insights, and it is fully optimizing for the new reality. You are advancing while everyone else is just trying to recover. Ultimately, the choice isn't whether disruption is going to happen. The market will always shift, systems are always going to face chaos. The strategic advantage shifts from building robust systems that survive disruption to building anti-fragile systems that improve because of it. So, thank you for joining me for this explainer. I want to leave you with one final thought to mull over as you look at your current AI pipelines. Are you building to withstand the storm, or are you building an engine that runs on the wind?